Check it out now, y'all.
NanoHub U, online instruction.
Hello and welcome to week 6 of NanoHub U's Introduction to Bioelectricity. I am Professor Pedro Irazzoki at Purdue University, and what we're going to talk about in this week are numerical methods of solving differential equations. So if you recall from the first 6 units in the course, we began by looking at the anatomy and structure of the nervous system and the peripheral nervous system, central and peripheral nervous systems. And we talked about how it's composed of individual cells, neurons, that signal to one another electrically. And how those electrical signals propagate, it was the subject of interest for the first 2 weeks, really, of the course, and looking at how you can build simple reflex circuits out of it, and how you can begin to understand more complex cortical processing. It's all based on these electrical signals. And so we dove in a little deeper at those electrical signals, and we began to ask if we could model them, and if we could model them with representative and equivalent circuits, which we did initially with a core conductor equation and equivalent circuit. And then we moved on to the cable equation and equivalent circuit, which allowed us to look at the way that individual neurons signal passively. So once we have an electrical signal in a neuron as a result of a postsynaptic potential, for example, how does that signal propagate through the cell? How does it attenuate in both space and time? And that's what the cable equation allowed us to predict. We then expanded on that and went into the Hodgkin-Huxley equation, which adds to the passive conduction, which the cable equation accounts for, by also accounting for active changes. So it looks at changes in impedance to various ions, the GK term, which looked at the changing membrane impedance to potassium ions, the GNA term, which looked at the changing membrane impedance to sodium ions, and so on. And by doing that, we arrived at an equation, the Hodgkin-Huxley equation, which fully predicts the electrical behavior of a neuron under a variety of different conditions. And in fact, what it allows us to do is make a series of predictions, or what it allowed Hodgkin and Huxley to do was make a series of predictions about how neurons would behave, which were then corroborated in the laboratory. So it turned out to be that very best kind of model, the model that predicts things we don't already know, and we then go into the laboratory and confirm those things to be true. Now, once we arrived at that, we took a sidestep and looked at applications of this information. So knowing how electrical signals are generated and propagating through the body, can we go in and can we begin to look at diseases like Parkinson's or epilepsy, or can we look at patients who are amputees, and can we begin to develop solutions, medical devices, that would allow us to modulate brain activity to cure them of their ailments, or allow us to record brain activity to control a prosthetic arm, for example. What I want to do now is I want to back up a little bit, go back to the Hodgkin-Huxley equation, and talk about how we solve that. So in the 4th unit, we talked about how that equation could not be solved analytically, and we left it at that. I mentioned that it could be solved numerically, but didn't say anything more. This week, I want to talk about what it means to solve an equation numerically, and go through various different ways of solving differential equations numerically. And by the end of this unit, you'll be able to write your own code to solve the Hodgkin-Huxley equation yourself, which will be very rewarding. So let's dive in. And before we go any further, I want to talk about today's lecture. I want to talk about discrete time solutions versus continuous time solutions. And solutions of what? Solutions of differential equations. So what is an equation? There are many different kinds of equations. The most simple form is the kind in which you relate a dependent variable, in this case y, to an independent variable, in this case x. So x can be any number of values, and for any value of x, you have a corresponding value of y. That is an equation. What is a differential equation? A differential equation is an equation in which we relate the derivative of the independent variable to the dependent variable. So a derivative or an integral, it doesn't matter. It involves the differentiation of one of the terms to arrive at what we call the differential equation. A second-order differential equation is where we have a second-order derivative somewhere in the equation. So we relate the derivative of y as a function of fx. In this case, is a function of potentially the first derivative of y with respect to x, and also x itself. An ordinary differential equation is an equation in which the derivative is all of the derivatives are taken with respect to a single independent variable. So in this case, on the left, for example, you have the derivative of y with respect to x is a function of the first derivative of y with respect to x and x itself, versus a partial differential equation, which is when the derivative of y with respect to x is a function of the derivative of y with respect to, for example, t, and also the derivative of y with respect to x. So we have derivatives as a function of multiple terms, x and t here. That makes it a partial differential equation versus an ordinary differential equation where all the derivatives are with respect to one variable. And then a homogeneous and linear ordinary differential equation is really one in which we can parcel out multiple inputs. And this is very important in the Hodgkin-Huxley case because what you're looking at is what is the response of a neuron to multiple electrical inputs. And so you don't want to solve Hodgkin-Huxley for all of them simultaneously. You want to solve Hodgkin-Huxley for one input, and then for another input, and then for another input, and then be able to add up all of those solutions at the end. And in order to do that, Hodgkin-Huxley needs to be a linear differential equation, which it is. And so what that means then, that linearity means, is that we can solve each of those inputs separately and sum up the outputs at the very end. And that'll be very, very useful in our applications of Hodgkin-Huxley. So the same classifications more relevant to the work that we're doing here. An equation is one which relates a dependent variable, in this case J sub m, the membrane current through an axon, to a series of independent variables, which are the currents through the various capacitive and resistive elements of that axon. The differential equation relates the first derivative of the membrane voltage with respect to time to in this case, the capacitive current, which it is. It's also related to the resistive current. And so that second order differential equation is that Hodgkin-Huxley equation that we talked about. Now this second order differential equation is a partial differential equation because it relates the second derivative of the membrane voltage with respect to distance along the axon z to the first derivative with respect to time of the membrane voltage. So it's a partial differential equation, which we can then use the wave equation, as we did in week 4, to convert to an ordinary differential equation where you have the second derivative of the membrane voltage with respect to time proportional to the first derivative of the membrane voltage with respect to time. And this is, in fact, a homogeneous linear equation because we can evaluate the output as a function of a sum of inputs, or we can take them individually and sum them after the fact, which is what we'll end up doing most of the time. So diving in, we have our equation, and we know, for example, that you've got, in this case, the derivative of y with respect to x, which is a simple example, is a function of x, and let's say it's a cosine of x. So what is y? We can solve y analytically and say y is the sine of x plus some constant c. So if you were to take the derivative of sine x plus c, you would get back to the derivative of y with respect to x is equal to cosine x. Fine. That's an analytical solution. What it means is that for any value of x, you have a corresponding value of y. Any value, an infinite number of values with any amount of precision that you care to put into the system, you're always going to get an exact corresponding value of y. Alternatively, you can have an equation like Hodgkin-Huxley, or the Cable equation, sorry, this is the Cable equation, which is a lot more complicated, but we can use the inhomogeneous diffusion equation to arrive at an analytical solution of that. And we did this in week 4. Fine. If you get to the Hodgkin-Huxley equation, what you find is that you cannot determine an analytical solution to that equation. Not every differential equation can be solved. And specifically, the Hodgkin-Huxley equation cannot be solved analytically. So instead of having a solution like we have for the Cable equation, where for any input value of time, for example, you can give a corresponding output value of membrane voltage, or for any value of space, you can do the same, you have what we call a discrete time solution, which means that you can solve y as a function of x at discrete points in time, but not in between. And so what we arrive at is, instead of having a continuous line which has a value of y for every value of x, we have a series of red circles shown here, where at those red points, you know what the solution is. But between them, you don't. Between them, we guess. We assume that nothing particularly exciting is happening between those discrete samples. And that assumption is based on something we call sampling theory. And we'll get back to that as well. But before we get there, let's talk about some new variables that we need to introduce in order to be able to solve equations numerically. So if we wish to arrive at a solution over a particular length of time in this case, but it can be time, it can be distance, it can be any independent variable. But in this case, it's a particular length of time. That length of time that we're interested in solving over, we're going to call capital T. the number of steps that we wish to solve over, we're going to call capital N. So if we want to have capital N samples of the continuous time solution as our discrete time solution, we're going to number each of those samples little n, where little n goes from 0 to capital N minus 1. Over the total interval, capital T, that means that the space between samples, h, is going to be equal to capital T divided by capital N minus 1. And that'll be the distance between the samples. 1 over little h will be the sampling frequency. And in this case, we're looking at solving the voltage, V, that's our dependent variable, as a function of the time t, which is our independent variable. So it's time to talk about sampling rate. So the key issue when you begin to solve equations numerically, or when you look at sampling anything really, not even just solving differential equations, but how do you select the settings for your recording amplifier, for analog to digital converter? The key issue is what we call sampling rate. What is that separation between samples? Recall that what we're going to end up with is a series of samples of the continuous time solution, and we're going to make the assumption, as I said earlier, that nothing particularly exciting happens between those samples. And that assumption is based on the knowledge that those samples are closely spaced, that they're close enough to capture everything interesting in our signal. And now you could say, well, then why don't we just make the samples really, really tiny, just make them super close, and then we'll be all set. Well, you can, but every time you solve, every time you have to solve one of those samples, it takes time, or it takes computing power. So when you come up and write your own code to solve the Hodgkin-Huxley equation, you can make h really, really, really tiny. But a couple of things will happen. First of all, your algorithm will take a very long time to run. And second of all, you'll introduce a series of other errors called round-off errors. But we'll talk about those more in the next lecture. For now, let's just say that the sampling rate is very important. And specifically, it's very important because we're worried about something called aliasing. So what is aliasing? Aliasing is the idea that we're going to sample here at time t equals 0, and then we don't know what we want h to be. We don't know how closely we want the next sample to be. So what if we just arbitrarily picked some value of h, and let's say h is a little bit more than the period of the wave that we're trying to capture. So we have our first sample here at time t equals 0. We have our second sample at time is just over 1 second. Our third sample at time is just over 2 seconds. So these are evenly spaced samples, and our sampling rate is much less than, or a little bit less than, the frequency of the wave we're trying to sample. If we were to then reconstruct the signal based on our samples, we would think that we were sampling a very slow sine wave. Right? So our idea of what it is that we're actually looking at is this very slow sine wave. We would not think that we were actually taking samples of this high frequency sine wave. We would instead think we had this slow frequency sine wave, and so our equation would solve. Our output would look lovely. We would plot it. We would see a sine wave, and we would go, ah, that's great. And it would turn out that our answer would be completely wrong. And we call this phenomenon of undersampling and reflecting a higher frequency signal as a lower frequency signal. We call this aliasing. And aliasing happens in all sorts of different interesting areas. If you've ever watched old cowboy movies, for example, you see the wagons going across the desert, and you see the wagon wheels, and they're spinning in one direction, and then they stop, they slow down, and then they start spinning backwards, and then they stop, and they start spinning forwards again, and you wonder, why does it look like the wheel is turning backwards? It's because the camera that is capturing the wheel's movement is doing so at a particular frame rate, a certain number of frames per second. And if that frame rate is not fast enough to capture the actual motion of the wheel, because it's turning faster than that sampling frequency, then you'll begin to get video aliasing. And it'll look like instead of the wheel moving quickly, it's moving slower, and perhaps even moving backwards. So we've all seen that in the movies. You can get the same sort of effect in an audio signal where a high frequency reflects as low frequency noise. So a high frequency noise that you cannot hear becomes part of the audible band, and you can get the same thing, importantly, in biomedical signals. So when you're looking at bioelectric signals, if you don't sample them adequately, it'll seem as though some of the high frequency components are actually signals, and you will interpret them as action potentials when in fact they're just aliased noise. So this is a very important subject. All right, so how do you get around it? There's something called the Nyquist-Shannon sampling theorem. And what the Nyquist-Shannon sampling theorem, or just the Nyquist theorem, says is that if you have a signal of interest, so this is your biological signal, this contains your signal unit action potentials, your group of neurons firing together as a local field potential, your very large group of neurons, millions of neurons firing together as an EEG, an electroencephalogram, they have some frequency band. And that band is limited, right? Neurons don't fire over all frequencies. They do so over some frequency band. In the case of neurons, that band is limited more or less to 1 kilohertz. And you can plot that frequency, signal as a function of frequency, and you'll see that you have your signals distributed in the positive and negative frequency domain from essentially 0 out to your band, which is for neurons about 1 kilohertz. Okay. So the Nyquist theorem says that in order to capture all of the data in your signal of interest perfectly, you want to sample at twice the highest frequency in your signal. So if the highest frequency in your signal is Fs, the signal frequency, you want your sampling frequency to be 2Fs or greater. In terms of signal reconstruction, there is absolutely no reason theoretically to make it greater than 2Fs, but we'll actually find that there are some reasons practically for doing so. So that's what the Nyquist theorem says. But what it doesn't account for at first blush, on first examination, is the presence of noise. So every signal has noise, and there's always different sources of noise, but one of the ones that you're going to find in every case is what's called white noise. And white noise is an evenly distributed noise as a function of frequency throughout all frequencies. And so white noise exists everywhere. And so if we come in now and we sample at twice the highest signal frequency, we're going to alias a bunch of the white noise that's out here on top of our signal. We're going to be adding noise to our signal and giving us the impression that we're seeing neurons that don't actually exist. So what we do is we filter. We take a filter and we make it so that the filter has a cutoff frequency that is right where Fs is, and then that filter will roll off at some steepness, depending on the order of the filter, how many filtering elements there are, will roll off and cut off the noise at that point. So after we filter the noise in this way, we get rid of the noise outside of the filter cutoff, and now we have a new set of frequency components. We have the ones that are of interest, which exist from 0 to Fs, and then we have the ones that exist between Fs and Fc. And the reason those are there is because in order to make this smaller, we would have to make the filter steeper, what's called a brick wall filter. And a brick wall filter introduces a whole bunch of noise in the time domain. We don't want to do that. So we make the filter less steep, which then means that we have this component here, which has to be accounted for. So our sampling frequency now, instead of being 2 times Fs, is going to be 2 times Fc. So something greater than. And for practical applications in neurons, we can look at the sampling frequency, which is 1 over h, the interval between samples, which is n minus 1 over t, has to be greater than 2 Fc, and we want this to be approximately 5 kilohertz. So let's say that your neurons are band limited to about 1 kilohertz. There's some information that can go up to, let's say, 2 kilohertz, and it varies from cell to cell, species to species. Let's say it goes up to 2 kilohertz. We have a filter that has a cutoff at 2 kilohertz and rolls off by 2.5 kilohertz. It's a fairly steep filter. You want to sample at twice 2.5 kilohertz. You're looking at a 5 kilosample per second, or 5 kilohertz sampling rate. And that's how we arrive at the actual sampling rate that you want to see in biomedical systems. So why, if that's the number, if 5 kilohertz is the number, why on earth would you ever want to sample higher than that? If you look at commercial systems, you'll see ones that sample at 10 kilohertz, 12 kilohertz, 20 kilohertz, 50 kilohertz. Sometimes it's just a sales gimmick, and sometimes there's a very good reason for doing it. So when you go to Best Buy and you buy a new television and they tell you need a 4K TV, fine. If you're sitting very close to it, you need a 4K TV. But if you're sitting 15 feet back from your television, the fact is that the sampling frequency of that TV, which is the pixels, right? The width of the pixel is the visual sampling rate at which the TV is sampling the actual image that it's representing. So if it's a photograph of your dog playing, that photograph has a particular resolution. And you put it on a 1080p television and you're going to get a particular sampling rate. You put it on a 4K TV and you're going to get a greater sampling rate. The question is, can you tell the difference? And if you get close enough to it, yes, of course, everybody can tell the difference. But if you're at a certain distance, is the sampling rate sufficient to fool the eye into thinking it is a continuous image. And so, well, that's a question I'll leave to you, but there's a fair amount of marketing involved as well. And this is how you tackle the salesman. You talk about Nyquist's sampling theorem and the ability of the eye to resolve specific individual frequencies at a given distance as a function of distance. But in bioelectricity, why do we oversample? So you oversample in many cases because there's no cost to not oversampling. So if you need to oversample at least 5 kilohertz, but your system is plugged into the wall and power is free, you're just drawing it from the grid, then why not sample at 50 kilohertz and just make sure you have everything just right? Because it's free. That's one reason to do it. It's not a very good reason, but it's a common reason. A better reason is because it makes the filtering for the anti-aliasing much easier. So if you sample at 5 kilohertz, that filter has to roll off from 2 to 2.5 kilohertz, and that's pretty fast, right? If you sample at 50 kilohertz, then the filter still cuts off at 2 kilohertz, but now it can roll off from 2 kilohertz all the way out to 25 kilohertz, and you're sampling at 50 kilohertz. That's a full 10 dB, or an order of magnitude further out in the steepness with which the filter has to roll off. It makes things a lot easier. A smoother roll off for the filter is easier to implement. It's a smaller circuit, but it also introduces less ripple noise in the time domain. So that's another reason to do it. And another reason to do it is that it allows you to improve the effective resolution. So if you're sampling at a particular resolution, a certain number of bits, if you oversample, you can average samples that are adjacent to one another, and you can essentially average out the noise component, giving you an effective increase in the total resolution. And it also allows you to lower the higher frequency quantization noise. So every time you sample, you have something which is called quantization noise, and that quantization noise is at the frequency of sampling. If you increase the sampling frequency, that noise moves out, it's further away from your passband, and it affects your signal of interest less. It also shrinks, because the change between samples diminishes if you sample more often. Why not oversample? There's really one big reason not to oversample, and that is because in an implantable medical device like what we talked about, Parkinson's and epilepsy, you have a limit in terms of your power budget, and we want to drive that power budget down. And that's why we want to sample as little as possible in implantable devices. So in the next lectures, what I'll talk about is, knowing what we know about sampling theory, how do we go about actually defining the solution for those individual discrete points, and why is that easier than solving for the analytical equation? And I'll see you then.